Okay, for this video, we'll be going through the practice paper 2. So this one is mainly on light. The other practice paper, I've already recorded the video, so it will be doing the current of electricity and DC circuit. Okay, so make sure you watch both. Okay, start with question 3. Diagram shows a patient having her eyes tested. So we have a chart with mirrors, with letters on it, placed behind her, and she sees the chart reflected in a plane mirror. So this is a plane mirror. We take note of the distance here. So how far from the patient is the image of the chart? So they are looking for the image, right? So if I were to treat this plane mirror as the center where the reflection is happening, so the image will be 5 meters away, right? 5 meters. So this is the image of the chart. Okay, but they are not asking for how far is the image from the mirror. They're asking from the patient. So it is 2 plus 5 because the patient is here, the image is here. So answer is D. Okay, question 4. A ray of light travels from vacuum into glass. So this is less dense. It's going to denser. So do you remember LDDT? Less dense to denser. It bends towards the normal. Okay, so if this is the incident ray, and if we draw the original path, we see that the light actually bends towards the normal. Okay, so if let's say they just give you like a vacuum and glass and they have a light ray like that, please remember to draw your own normal. Okay, normal is very important. Now what's the refractive index of the glass? Okay, so we have done there's this formula, N equals to C over V. Okay, so this one is actually telling you that the refractive index is actually a ratio of the speed of light in vacuum, and the speed of light in the medium. So the V is for the speed of light in the medium. Okay, the C represents speed of light in vacuum. So they want us to find the refractive index, and we actually see that this is V1, so this is the speed of light in vacuum. So I will have, they want us refractive index of glass, right? So N equals to speed of light in vacuum is V1 over V2, and we straight away have this answer of C. Okay, but how about if we use our N1 sine theta 1 equals to N2 sine theta 2, because we see that there's actually sine P over sine S and sine Q over sine R lah. Okay, first of all, P is the angle of incidence and R is the angle of refraction. So we see that this is P over S, so this is definitely not correct, right? Because the angle must always be measured with respect to the normal. Then the other one, we see that we have Q, which again is not the correct angle to use because it must be measured with respect to the normal, versus R. So this one is correct, but this is incorrect. Alright, therefore both answers are out. So but if we use the correct values, let's try using this formula. N1 sine theta 1 equals to N2 sine theta 2. The beauty about this formula is that you can choose any of the medium to be either 1 or 2, which means for this case, vacuum, I choose it to be 1. And you must know that the refractive index of vacuum is 1. That's the minimum value of refractive index, which means to say, if you get a if you do your calculation and you get your refractive index to be less than 1, you are wrong. Okay, that means somewhere in the formula you substitute wrongly. So refractive index of vacuum is 1 sine theta. Theta, we have to use this angle P, right, because it's in the medium one. So N2 is the refractive index of the glass, so this is N2 sine R, right? I hope you can see from here. So therefore N2 will be equals to sine P over sine R, which is none of the options here, right? Okay, question 5. A human eye has a converging lens that produces image at the back of the eye. Okay. What type of image is produced on the retina when the eye views a distant object? Okay, so actually if you look at your different cases of lenses, there are 6 cases, right? For the eye, it will produce a inverted, real, and diminish. Okay, for distant object, like let's say if I'm looking at a very tall building, the actual building is actually like maybe 40 meters in height, but this image can actually be formed within my eye. Okay, so it will definitely be diminished, and because it is able to produce an image at the back, right, that means it's able to be captured on a screen. That means it must be real. Anything that can be captured on a screen, it is a real image. For virtual image, it cannot be captured on a screen. Then I told you in class, inverted always goes with real. Okay, upright always goes with virtual. So answer will be B. Okay. Okay, state 3 characteristics. I think you can find this in the notes. Now, figure 4.9 shows a triangular object ABC placed in front of a plane mirror. By drawing 2 rays, complete the ray diagram to illustrate how the eye sees the image of corner C. So we are only focusing on corner C. We did this quite a lot in class already. So first of all, you draw a normal to the mirror. And remember, normal must be perpendicular to the surface. And then we continue this normal with equal length to find the where is the image. Okay, C or C prime lah. Okay, now of course the use of a mirror is for us to look at the image, not the object itself. So I now need to draw 2 rays, okay, because one ray will go to the top of the eye, the other one will go to the bottom, so they must enter. So I'm looking at this image here. So next step is I will draw light ray. Okay, 2 of them, okay, that enters the eye. Okay, so why is it dotted here? Because there's nothing in behind the mirror, because it's imaginary. There's nothing there, so we have to use dotted lines. But actually, where does the light ray come from? So far I've done these 2 steps. The first step is drawing a normal, then equal distance to the mirror to locate the image. So this is my step 1. Step 2 is actually from the image that I've located, draw the light rays to the eye. Step 3 will then be from the object to the point of incidences. Okay, because that's where the light ray comes from. But you may say, how come this triangular object can give out light ray? Because there must be light around it. Right? When you go into a room and you can see something, there must be light switch on, or there must be a source of light, right? The source of light will project a light onto the object, and the object reflects the light into our eyes, correct? So you don't actually need to find out, oh, is there a lamp somewhere, or is there the sun somewhere? No, you don't care about it. Okay, if there's no light source, you can't even see anything. There won't be any reflection in the mirror. Okay, 6.1 shows the position of an object, a thin converging lens, and the image produced by the lens. Draw 2 rays to complete the ray diagram. So I want to illustrate this point that the lens is here. Object is traditionally on the left-hand side of the lens. Left-hand side, for O-level, left-hand side. So if the image which is given here is found on the opposite side, it will definitely be inverted. It will definitely be real, because I and R comes together as a pair. But now if I have the image, if I tell you, oh, image is actually found on the same side. Okay, if image is found on the same side as the object, then it will definitely be upright. It will definitely be virtual. So this is our UV. Okay, but since for question 6 they tell us that the image is over here, we'll focus with this. Okay, so this is actually no longer required in our syllabus, but it's good that you know. So there are 3 light rays that can actually help us to locate where the image is. But since now they tell us that the image is there, we will just draw our light ray. The first one is, let's say we start with the tip, yeah? It will pass through the optical center without bending. So if you have your hard copy notes, right, you can actually draw a straight line using a ruler that passes from the tip of the object through the optical center and touching the tip of the image. Okay, I'm sure you can do that because we have done this using we set this question, and of course we must be able to do that lah. So this is the first light ray that you can draw, and this is actually one of my favorite light ray because it just passed through optical center without bending. The second one is the light ray, okay, which is parallel to the principal axis, will touch the lens, and then it will go and cut the F. What is F? F is the focal point. But then you say, but how do I know where's the focal point? You don't know. In this question, you don't know. But in some questions, they give you the focal point. So example, if the focal point is here, the light ray will go down and cut the focal point. Okay? But because in this question, no focal point is given, but I know that this tip, this light ray that comes out from the tip of the object must go on to form the tip of the image. It must, right? So where it cuts the focal, where it cuts the principal axis will then be my focal point. Okay, and each lens actually have two focal points, one on each side. So if I have this focal point here, this will be my focal length. Okay, so I must have another one of equal distance. Okay, of equal distance on the other side. So this is my second focal point. Okay, so this is my second light ray. I say again, how do I get my second light ray? The light ray that comes from the object, which is parallel to the principal axis. Of course, there are multiple light rays coming out. But so far, I have only introduced two light rays. The one that passes through the optical center, which I always can predict its behavior. It's going to pass through optical center without bending. So this is my ray number one. Ray number two is the one whereby if it is parallel to the principal axis, once it touches the lens, it will definitely go on to cut the focal point. Okay? How about all these three? I wouldn't know. I only know after I have known where is the image. After I know where's the image. Okay, but before I know where the image is, it cannot, I'm not able to predict how it will go on to go and meet the image when I don't even know where the image is. Okay, I hope you understand what I'm trying to say here. So the third light ray that I can definitely predict its behavior is the one light ray that cuts the focal point on this side, and once it cut, it will become parallel to the principal axis. So these are the three light rays that I am very confident I know how they are going to behave. The other light rays that come out like that, I'm not able to predict. But these three, 1, 2, 3, I definitely know how they will behave if they follow the rules. Okay? So this is part 1. Draw 2 rays from the object. Mark and label the focal point. So this is the focal point. Done. Define focal length. So it's the distance between focal point and optical center. Okay, where's the optical center? It is where the lens and the principal axis intersect. What's an application for this? So this one can be a projector, because you see, are you able to measure the height of the object versus height of the image? Right? So actually the height of the object is lesser than the height of the image. That means this image, besides being inverted and real, it is also magnified. Okay? So this is all for this practice paper.